Assalamu alaikum warahmatullah. Today we have new experiment, tray dryer experiment. Tray dryer experiment is a technique used to dry products in pharmacy, in agriculture product, and it's used by chemical engineers and by production engineers, by agriculture engineers to get rid of water before from the product before its final packing. So as you know, if I have a product, any product, you can assume this product is like fruits, vegetables, pharmaceutical product, or even anything, and you want to minimize the amount of water in this product in order to reserve it and kill the microorganism. So now we can dry it by air. So if I have air, and this air, suppose that it 30% the humidity of the air. So, and if my product is 90% of the water content in the product, so when it reach equilibrium, you might assume that it should reach 30%. Okay, but actually it doesn't reach this value. It can reach to a value higher than what you expected, like you can reach 70%. Why? Because the structure of the cells and the structure of the pores, so it have limited the equilibrium between both. So now we have a total, this is total, and the final humidity that reach at the certain income air condition, so it's free, so it's difference between them, and equilibrium. So this is the equilibrium. Okay, the difference between equilibrium and the initial condition is the free. So we have the humidity, free humidity, equilibrium, and total. So here we can, if we take this example, so now the humidity, total humidity is 90%, the equilibrium is 70%, and the free is 20%, the difference between them. So each product has its own equilibrium humidity. So suppose that this is a curve represents the air on y-axis, air humidity, and we have x, that means solid humidity, whatever the solid type, at certain pressure and temperature. So we have here we have certain temperature and certain pressure. Only the difference is the air humidity. And we have like different product. Suppose that we have a wool and we have a paper. So at the same certain air humidity, we have different solid humidity, equilibrium humidity. Okay, so that means wool can acquire more moisture than paper do. Any amount in wool after this value, it's called free moisture or bounded or free water or unbounded water. Any value before this value at certain air temperature, it's called equilibrium humidity or bounded water. And as we said, it's because if we have like a cellular, or we have a port, so this retains some water inside and prevent it at certain conditions. So this is called equilibrium. Okay, but if I have loose solid, like you have like a sand, for example, sand or different pellets or anything loose, so the humidity of air will be the same humidity because it will be dry, so the surface will be exactly the air humidity. Actually, this is for the X total. So now, in order to determine the R, the rate of evaporation, it has three parts. Initial part or preheating part, we have constant part, and we have falling part. And that part, the point that differentiate between constant and falling, is called critical point. So rate of evaporation can be plot against time or against humidity. So what is the definition of R? R is the drying rate. So it's very important for engineers to design the rate of drying for their product. Rate of drying or drying rate equal to rate of vapor per drying area. So suppose that I have a tray, and this tray has a width and length. So this will be the drying area. And if I have a product here, my product, I put my product here. So the rate of vapor as per the incoming air properties. So as we said here, we have initial again, constant and falling. So suppose that this air is, we have like certain temperature and humidity, and the exit has temperature and humidity. So when the hot air come over the tray, first some sensible heat will be acquired by the solid. So the solid will acquire some sensible heat. And this sensible heat will be also lead to some latent heat, and vapor will start to increase a little bit. Some vapor will increase. So now you will see that rate of evaporation start increasing until all water content in the solid through the surface area will be vaporized. So this water through all the surface area will be vaporized. So the rate will be constant. Why constant? Because the vapor will cover all the surface. So it's my limitation is the surface. So, and when the vapor move to the atmosphere, it will be compensated by another water, because we have, when you have a port, we have like a capillary tube. So when vapor move out, it will be compensated by another water from the sublayer. Okay, so as water on the surface, top surface, it vaporized, another water will be replaced the top surface, and so on. So this surface will be constant. So the drying rate will be constant until a point that no more water can compensate for the capillary tube. That means this part or this patch of part will be dry. So the evaporation happens through the surface except this point. At this point, I will start my first drying curve. Then another point will dry out. Then the drying area or drying batch will increase. So the drying rate will decrease until no more water in my tray dryer. So at this, the rate reach to 0. So this is the principles. Now, how to determine the rate of evaporation? We have two ways to determine the rate of evaporation. We can determine the rate of evaporation through analyzing the air properties before and after. So I have air enter the tray, and this air has a specific humidity and specific temperature. Then it exits by specific temperature and specific humidity. So the difference in humidity between them, that means this air already carry some water from the dryer, from the solid. So this is the amount of water carried by the air. So I can determine the humidity, the rate of evaporation through the air properties. Also, I can determine the rate of evaporation through the weight loss of the solid. The solid already have water inside. And after some time, this weight become less. And this, of course, the less due to water, not due to the solid. So when water evaporate, the weight become less. So if I can take the difference between two solids weight at certain time delta T, so I can determine the rate of evaporation. So now let's apply the first method. Now we said rate of evaporation equal mass flow rate of vapor over the drying area, and this is the drying area. If you have only one tray, then it will be the surface area of one tray. If you work on multiple trays, like 2 or 3, then the surface area of one tray times 2 or 3. So this is the tray area. So rate of evaporation equal, we want to determine the difference of humidity between the exit air and inlet air. And it's equal to mass flow rate of dry air times air humidity after or post the trace and humidity pre the trace. So if you take we have probes, we'll see in the equipment, we have probes before and after. So this probe measures the temperature and the humidity. So if we determine the XP minus XA over A, and now how to determine XP and XA? We can determine it by using psychrometric chart. The probe here measures something called relative humidity. And here X should be in terms of mass fraction or absolute humidity. From psychrometric chart, this is the relative humidity. So when you take the dry temperature and relative humidity, you can determine the absolute humidity for the inlet air and for the outlet air and for the inlet air. Now, mass flow rate, as you know from fluid mechanics, equal velocity times area times density. And area here is the cross-sectional area. So it should be the air passed through the duct or through the tunnel of the drying. So we have our tray inside. So all this, the cross-sectional area of the tray dryer is here. And you have to differentiate between A here and A here. Here is the air of the cross-sectional area of the tunnel. Here is the area of trays itself, because it's drying area, times rho. Rho is the density of air. You shouldn't calculate the density using ideal gas law because it's wrong, but you have to, because the air here is moist air. So that means air have some water inside. So in order to calculate the density correctly, we have used psychrometric chart. From psychrometric chart, we have something called specific volume, and specific volume equal 1 over density of air. So here's specific volume. So you can find the specific volume of inlet air, specific volume of outlet air, and the average of them is the specific volume of the air. So here it will be rho will be down here, specific volume. So we have here again the speed of air or velocity of air. We have cross-sectional area of the duct. We have drying area, and we have specific volume and XP minus XA. So all these properties can be found from psychrometric chart. Specific volume, absolute humidity at the exit, absolute humidity at the input. And these properties, other properties, A and A is given from the lab manual, V is given from the raw data. So the raw data given, you have a time, you have velocity, you have temperature and relative humidity pre the trials, temperature and relative humidity post the trials, and you have the weight. Okay? And this weight is total weight. Total. That means weight of trays, all trays, plus solid, plus water. Total tray. So the weight of tray and solid and water inside the solid. So this is all your raw data. Now we want to determine, okay, we want to determine the flow rate, the drying rate. So now from V, the velocity, okay, you have temperature and relative humidity, then you can use them to find the absolute. Also T and relative humidity, you can find them to find. So you can apply it for initial condition if you want to find the flow rate, the drying rate for initial condition, or for the constant condition, or for the falling condition. So this is initial, constant, and falling. Since the constant condition is characterized by constant constant rate of evaporation, so you can, this part for constant is fixed. Not time, sorry, I mean this is a velocity and time, relative humidity, time, relative humidity. So these three properties are constant. So you can take the average of velocity, and put it here. You can take the average of T and relative humidity to find the input X from psychrometric chart, and you can take the temperature and relative humidity for the output to find the XP, the absolute humidity of the outlet air. By this, you can calculate rate of drying using air properties. Now, we can also determine the rate of evaporation from the solid itself, as we said, through the water lost from the solid. Now, rate of evaporation, if I have initial solid, and then we have the weight of another solid, okay? So here we have weight, and this weight per time. So each time, okay, we have different weight. So this weight decrease per time. And the decreasing in weight is due to the evaporation. So if I take the weight, solid 1 minus solid 2 over area of drying times T2 minus T1, the difference in time, I can find the rate of evaporation. So this is the wet solid 1 minus wet solid 2. Now we put a minus here because it should be MS2 minus MS1, but because MS1 is higher than MS2, so we put the minus here. Now, S is the dry, this is the dry solid. So dry solid times delta X. Delta X is the, you have here to differentiate between X of air and X of solid. X of solid is the moisture of the solid or humidity of the solid. So it's equal to kilogram of water per kilogram of solid. So it can be determined by wet solid minus dry solid. So if you have wet solid minus dry solid, so it's kilogram of water per dry solid, so it's kilogram of dry solid, so it's kilogram water per kilogram dry solid. So here X is for solid, not for air, per delta T, or the time. So and if you want to make it for differential equation, so it will equal to minus S over A times dx over dt. Now, if you take the raw data from the experiment, time and W, and you plot them, so this is the weight and this is the time. So if you plot them, you have a curve like this. Okay? The weight here is the weight of dry solid plus trace plus water. So and the decreasing is due to the water evaporation until the weight become constant, so there is no decrease. So this will be the weight of dry solid plus tray. I have no more water because water already evaporates and it's constant. So this is a dry plus trays. If you already know the weight of empty tray, so if you got empty tray, empty tray, and you weigh the empty tray, so you can determine the amount of dry solid. So first, take this value. This value represents the dry solid plus the tray. Then you can, from the weight of trays, if you have 2 trays, you have to cancel 2 trays from this value. So you have the dry solid amount. Now, okay, how to calculate X? Calculate is the wet solid minus dry solid over dry solid. So then X here you can calculate wet solid. Okay, now you already have this weight. This is total weight. Okay, total weight. Then you can calculate Y of water. How to calculate Y of W of water? W water weight. So now we already determined the amount of dry, and you already know the tray weight. So water will be this weight minus tray minus dry solid. Okay, so it will give you only the weight of water. Then create another column. We'll go down here. This column X, and X represents the humidity of the solid. So it will be water over dry solid. Water, this column, the previous column, and dry solid. Okay. Then you can plot X, this column, against time again. So you almost get similar plot like this one. Okay, because the dry and tray are constant. So this represents X, soil or solid humidity, and time. So you can get curve like this. Now, this curve, you can split this curve into 3 parts. The first part is polynomial. Second part is constant. Third part is polynomial again, or like this. So polynomial, constant or linear, and polynomial. So this is linear and polynomial. Now, if you can differentiate, for example, this is from time 0 to time 30. Okay? And this from time 30 to time 60, for example. And from time 60 to 120. I'm just giving examples. So now X and time, okay? So you can differentiate. This part is for initial. This part is for constant on the Excel sheet. And the third part for falling. Okay. Now plot X and time alone for the initial. So you will get a curve like this. This curve is polynomial. So its line, its regression line, A dot plus A1x plus A2x squared. For the linear, its regression line is A dot plus A1x. For the third one, it will be A dot plus, or A naught plus A1x plus A2x squared. Okay. Now we can differentiate this equation because we want to find dx over dt. dx over dt, so we can differentiate this equation. So this equation will be A1x times plus 2A2x squared. X, sorry, not squared. Okay? since the x is t, okay, so it will be a1 times time plus 2a2 times, okay, sorry, I did a mistake here. It should be here, here, a1 plus 2a2x. Okay, so here it will be a1 plus 2a2 time. Okay, take care because some students do a mistake and for the x they make it for the humidity. No, it's for function of time. Okay, and here, okay, the differentiation of this equation, it will be only a1, and for the falling it will be a1 plus 2a2x. So it will be a1 plus 2a2 time. So now we can find dx over dt. For the initial, you already have the differentiation of this equation. Okay, so a1 plus 2a2 time. So you can find dx over dt. For constant, it's just the slope. So just put the slope. And for the falling, you will do the same. Now you can find the r equal minus dry solid over area of trace times dx over dt. So you will find this part will or this part. So finally, when you plot the time r against time, you get curve like this. So this is the initial, constant, falling. Sometimes you don't have initial, you only have constant and falling. So it's usual. You may have only constant and falling. Okay, if already the tray dryer is preheated well and you have not too much water, so you can start from constant to falling, and this point is critical. Okay, so then you can compare the raw data, the rate of evaporation for the constant, with that one you got it from air properties and find the relative error between them. So this is all about the theory for the experiment, and we can go for the experiment itself. Now we'll start the experiment. We have the tray dryer. This is a lab tray dryer. So we have here, we have like something like a balance to weigh the trays. So we have 3 trays. This one is empty tray. Just we will use it to weigh the empty tray. And we have trays with sand. Okay, so after first we should calibrate the balance and make it 0 on the software, and then weigh the empty trays, and then we can take, we have 2 options, either to determine the dry weight of the soil or of the sand and then put water and then measure it again, but we don't prefer it because sometimes the sensitivity of the balance is changed by time, by the effect of heat, so you can get some error. So that's why we depend on calculating the dry solid by the, as from the chart, as we said, when it's come constant, we take the amount of dry solid, as we said, because the sensitivity is different. Also here we have like a probe. If you can see the probe before and probe after. So the probe before is to measure the relative humidity and the temperature pre the trace, and the other one is post the trace. Also we have this orange one, is just to distribute the air among the trays. So we can, just to see, we can put the trays here. Okay, and close. So this is what we will do later. Okay, I will remove again. So before doing this, we have to adjust the properties of the software. So now we'll go to the software to see what we should do. now this is the parts of the trays. We have a fan, and we have the trays, and here you have two props, temperature and relative humidity post, and temperature relative humidity pre. So, and this is the trays, this is the weight for trays, we have 3, okay, and this is the total. So it's very important to make it 0 first, okay, to make it 0, okay, 0, 0, 0, in order to make total mass 0. Okay, now let's set the temperature. So from configuration here, here we can set the sampling time. How the sampling will take every 10 minutes, every 10 seconds, so as you wish. So I will make the intervals every 10 seconds, okay, automatic or manual. Automatic, that means every 10 seconds directly take the reading. Manual, you have to press every time. So I'll make it continuously, okay. Also ask for continuous or for fixed duration. For me, I prefer to make continuous because I want to check once it reaches the stabilized weight, I can stop it. So, okay. Okay. Also, we can here go for the PID. Okay, this is for temperature. This is the set point, this is the temperature. You can set your temperature of the oven. So let's make it 50, for example. Okay, and make it automatic. So that means once the sensor feels there is a difference in temperature, so it set it again to 50. Apply, and okay. So now we can make here, we can start the power on, okay, but before start the power on, we should calibrate the air velocity, make it 0 as well, okay, and then first close the door, the gate of the equipment, okay, and then here we can make power on, okay, and fan speed is 0, increase the speed. So it was a little mistake, but that's because the communication was not connecting. So thus I pressed here and make the connection. So now it works. Okay, as you can see now, the temperature is reading, and temperature is reading, humidity is reading, and also the velocity. And here we can increase or decrease the fan speed. Again, we try to minimize. Of course, it can be fixed. Like there's some fluctuation in the data because air is flow over the trays, so it affects on the mass. Okay, but at least we try to make it reach the minimum as we can. Okay, so now we set the temperature. Now the initial temperature is 45. If you remember, we set it as here the heat is 90. Is 50, sorry, but the air makes some cooling for the heater, so it's starting, or the pre temperature of the air is 47, okay, but after some time it reaches to 50, okay, and here we have the velocity. You can increase or decrease according to the fan speed, okay. So now we'll start our experiment by put some water on the sand. So we will work only on 2 trays. So during calculation, you have to make sure that the trays area is 2 trays. So cover it with water. You should make sure that the surface is totally covered by water. Okay. Also here, so now the surface is totally wet. We can put our trays Okay, and then back again to the software. Now the total weight is 170 or 80. So you can just wait for a few seconds until almost stabilized. Okay, and then you can press go. When you press go, it will start measure the time and the weight and take all data. So we can make go. Okay, now we can go for the here. This is a plotting shape. So it takes the first time. After now it takes the second one. So every 10 seconds it will take new point. If you want to check the data from the curve, of course the first 2 or 3 data is not, because it's not stabilized, so you can find some scatter point. But as you can see, it's increasing. Okay, as we said, we have initial, then constant, then falling. So here for the Excel sheet, this is the elapsed time. This is sampling time. This is not important column, but you have to know what the exact time. So this is elapsed time, 1, 2, 3. It's number 1, 2, 3, 4. So if you make the setting as 10 seconds, like we did, so you can here make equation for the real time, 1 times 10, so 2 times 10, and so on. Heater output is not important. Here the important is temperature. This is the dry bulb temperature and relative humidity. This is for the pre-trace, before the properties of air before contacting the surface. And we also have the temperature post-trace, relative humidity. Okay. We also have the fan output, inlet velocity, trace velocity. So this is the calculated tray velocity, because this is the velocity over the tray. So it's the most important one. And total weight. Okay, this one is not important for me. So this is my total weight. Okay, so now let's go check again the still it's scattered. Okay, some scatter point, but still become more clear. So the experiment may take about 2 or 3 hours until the curve becomes stabilized, but finally you will get a curve like this. This is from real data. So this is the same previous data we already did it before. This is the table. Okay, and we will get a curve like this. So now this is initial, constant, and falling. Falling, you can start from polynomials. You can start from here. Okay, and now the weight is almost constant. So you can extend the line here. Okay, so this will be the weight of solid, dry solid plus the trace, and you can calculate the amount of dry solid from this point, and then you can do your calculation. So this is all about experiment. The last thing, you have to make sure that after the experiment is finished, so you can make stop, power off, and save data. So to save data, save as. Okay, and choose your file extension Excel. Okay, and put your name or the session name. Okay, so that's it about the tray dryer experiment. Hope you found it useful and easy, and see you in another experiment, inshallah.